So in the last lecture we started with the wave function, the time dependent wave function psi given by psi naught e to the power I over h bar not kx p dot r minus et. Okay. We called it trial wave function, but I think this is more kind of explicit. We are trying to explicitly write the wave function, but we are not confirmed about this value, so it's basically not completely explicit. Okay, so basically we can call it as Ansatz wave function. Because the structure basically we you can call it as an assumed structure is there. So that there will be a psi naught and this exponential part we have already discussed, and we will further discuss about this in our coming lectures, how we can estimate that this can be the wave function. One of the reasons is that if you put this wave function, earlier we have already done this, that if you put this wave function in the Dirac equation, then you will find that it is satisfying the both hand sides. Okay, so and we arrived at some of the results, like when we wrote it in the form E equals p square c square plus mc to the power 4, and when we replaced E by I h bar del over del t and p by minus I h bar del over del x for one dimension, but for our case minus I h bar nebula. Okay, so when we replaced this, we got what we got. So we got a few results about we got E equals C alpha P plus this is, there is m square term, plus beta m c square. So for this alpha was alpha I, which was alpha x comma alpha y and alpha z, and then beta is also a matrix. Okay, so and we found about some of the relations between this alpha and beta, and what we got was the first thing is that alpha I square was 1, beta square was 1, and alpha I was also alpha I dagger, and beta was also beta dagger, that is, it was Hermitian in nature. And we also got this result that alpha I was alpha I inverse, and beta is also equal to beta inverse. Okay. Then we arrived at this result also, that alpha I beta is equal to minus beta alpha I, valid for all the x, y and z. And then we calculated the determinant, and we got that minus 1 to the power n was 1 equals 1, and that gave us that n should be even. Okay, and this forced us to assume that the matrix must be having even number of rows and columns. Okay, then next what we are going to do is we have to check the trace of the matrix alpha I and trace of matrix beta. Okay, so let's check this. Okay. These two things will be 0 because of the fact that alpha I beta is equal to minus beta alpha I. Okay, and you can check this by taking starting from here. So let's just check this. So alpha I beta is equal to minus beta alpha I. So if I multiply both hand sides by alpha I inverse, okay, so let's see what happens. Alpha I beta then alpha I inverse equals beta minus beta alpha I inverse. Okay, so these two will give you unity, and we can write it as alpha I beta alpha I inverse equals minus beta. Okay, so now if you take the trace on both sides, this will give trace alpha I. If some of you are not aware of what is meant by trace, then trace of any matrix, okay, A B C D E F, like this, any matrix G H I. Okay, so the trace is given by the sum of the diagonal terms. Okay, so for this matrix the trace will be A plus E plus I. Okay, so alpha is a matrix which is a 4 by 4 matrix. We have already seen this. Okay, and further we will see it. So the trace of the left hand side, alpha I beta alpha I inverse, will be equal to trace of this minus beta. Okay, now there is a theorem from algebra, matrix algebra. You know that trace of three matrices, the product of three matrices A, B, C, can be written in a cyclic order, that like A, B and C. So you can replace in a cyclic order, and then it can be, if you take C as a first term, okay, so C then A then B. C will come from here, and we in cyclic order you can replace one by one. So these two are equal. So in the similar manner we can take this term in the left of this. So we can write trace of alpha I inverse alpha I beta is equal to trace of minus beta. So these little manipulations of algebra will give you nice results which can be used in our formulation. So this will be 1. So simply trace of beta will be equal to trace of negative of beta, but you know that negative of beta will put a minus sign on every term, and if there is a minus sign on each of the terms you can take it out. So in that manner we can write it as trace beta. Then we can simply write that twice of trace beta will be 0, or simply trace of beta is 0. So this one we have already proved, and in the similar manner we can also prove that trace of alpha I. Let's do this, because studying a theory is a good thing, but you need to develop how to go step by step, and very clearly you should be able to do all the mathematical calculations. So let's do the next one, that trace of alpha I is 0. So for that we can start with the same argument, this one. Okay, so alpha I beta equals minus beta alpha I. So previously we multiplied it by alpha inverse from the left hand side. So this time we will multiply it by beta inverse. Okay, so if I multiply both hand side by beta inverse, so alpha I beta, then beta inverse will give you minus beta alpha I beta inverse. Okay, this implies this will be 1, so alpha I will be minus beta alpha I beta inverse. And if I take the trace of alpha I will be negative of the trace of beta alpha I beta inverse, and you can write this using the cyclic order, minus trace of beta inverse beta alpha I. This will be trace, this will be 1 of alpha I, so negative. So this implies, if you take in the left hand side, the trace of alpha I will be 0. So these are the two more important results we have got. So now let's see what we have come with. So we can say that after writing the energy expression in the form C alpha P plus beta m C square, after writing the energy expression in this form, we have assumed these matrices alpha I and beta, and we have relations which we already listed, including the two new. Okay, so let's give some numbering and write all the relations. So first one was alpha I dagger is equal to alpha I, and beta dagger equals beta. Okay, so there is necessity to list all once more. Okay, maybe some of them may be missing, so let me write once again all of the relations. So alpha I square equals 1 and beta square equals 1. This was the second. The third thing we have is alpha I equals alpha I inverse, and also for beta equals beta inverse. Then we have that this also implies that alpha I and beta are non-singular. That is, the determinant of alpha I is 0 and determinant of beta is not 0. Okay, these two are not 0. Okay, and in the fourth condition we have that n is even. That means the at least the matrix, the order of matrix of these matrices alpha and beta, at least there should be 4 by 4 matrices, not less than that. Okay, then the fifth condition we have is the trace of alpha I is 0 and trace of beta is also 0. Okay, and this was imposed because of alpha I beta is equal to minus beta alpha I. Okay, so juggling over all these conditions, okay, it can take some time for someone to visualize that what this alpha and beta can be. So people have think, especially Dirac must have thought what this alpha and beta could be. Okay, so because we know that in 2 dimensions, one of the most important results which can give the structure of the matrices alpha and beta can be arrived from this result, that we know that in 2 dimension, okay, the polymatrices sigma which are sigma x given by 0 1 1 0, sigma y equals 0 iota minus iota, okay, and sigma z equals 1 minus 1 0 0. These are the matrices in 2 dimensions which satisfy this kind of result. Okay, so maybe we can use these matrices to construct a matrix in 4 dimension, and it really works. So the matrices alpha have a structure like this: 0 0 sigma I, and this is also sigma I. Okay, and beta is given as identity matrix 0 0 minus of negative of the identity matrix. So basically this is a 4 by 4 matrices. This is also a 4 by 4 matrix. What we have to do is replace this I. Suppose you wanted to write the alpha x. Okay, so you will write 0 sigma x then 0, and then we have to expand the matrix sigma x first. Okay, so sigma x we can write it as, what is sigma x? This one. So 0 1 1 0. Okay, and here also we will write 0 1 1 0, and rest of the terms will be 0. Okay, I think there is a mistake in writing it, so let me erase it first, because I need also one. So for this 0 we will write these 4 zeros, and then I will write this 0 1 1 0, and then the 4 zeros. So this is sigma x and this is sigma x. So this is alpha x, And similarly we can write, let's write all the terms. Okay, so alpha y will be, we will write the y term, sigma y. So this will be 0 0 0 0, then in this term. Okay, so 0 minus iota iota, and then 0, then 0 minus iota iota, then 0, and then 0 0 0 0. So this is sigma y. And similarly we should write the not sigma y, alpha y, and we can write alpha z also. Okay, so alpha z will be, so you know that we have the sigma z as this. So first we can write 0 0 0 0, then sigma z, which is this one. Okay, 1 minus 1. So first we have to write 1, then minus 1, and then 0 0. And then here also we have to write 1 0 0 minus 1 0 0 0 0. So we have wrote alpha x, alpha y, and alpha z. And lastly we can write beta. The structure of beta is 1 0 0 1, not 1, I minus I. Okay, so this was beta. So we can write it as 1 0 0 1 identity matrix, then 0 0 0 0. Okay, so and here also 0 0 0 0, and then minus 1 0 0 minus 1. So we have replaced the identity matrix in 2 cross 2 here. Okay, with a minus sign. So these are the alpha and beta matrices which is derived from the, when we wrote Dirac the energy expression in the linear form. Okay, so why actually this can be these are the matrices. We have not actually arrived at this solution. Okay, we have certain conditions which is listed in these 5 points. Okay, and including this also. So the matrices, the 4 cross 4 matrices of alpha, I, and beta, which can be a possible solution to this, was estimated using the 2-dimensional condition of the polymatrices. We know the properties of the polymatrices, how they multiply. Sigma x and sigma y gives you minus sigma y sigma x, and this thing was utilized. And any matrix in 2 dimension can be written as a linear combination of all the 3 and the unit matrix. So for the simplest case, this can be the results in 4 dimension. Okay, so this was taken as the possible solution, not the possible structure of the alpha and beta matrices. Okay, so now let's again start with the energy expression E equals C alpha P plus beta MC square. And now again do the first quantization, which is writing E as I h bar del over del T, and this P as minus I h bar del, and let's see what happens. Okay, so you know we have already written this 2 times, so just write, okay, bar del over del t, but we have to apply it on some wave function psi, okay, equals c alpha and then minus I h bar del plus beta mc square acting on some wave function psi, where psi is a function of r and t, not x and t, because already we know that this is a 3-dimensional case, r and t. Okay, so now let's apply these operators. Okay, so this will be I h bar. So now you know the structure of this psi we have already discussed. So we can write it as, now we can do a little manipulation here, that del over del t, left hand side it will be same, and r comma t, and let's write in a simpler manner, minus iota h bar c and then alpha delta, not delta, del plus beta mc square, okay, psi r comma t. Okay, so what we are going to do is we will be multiplying, let's call this first equation number 1. Okay, now what we will do, we will multiply equation 1 by the conjugate of the psi, which is psi dagger. Okay, from left hand side we will always put the dagger terms from, multiply the dagger terms from left hand side. So let's multiply by psi dagger. Okay, so it will be I h bar, these are constants, so this is psi dagger del psi over del t. Okay, so this is the left hand side, and let's multiply by psi dagger to this term. Okay, so it will be psi dagger and then minus iota h bar c alpha del plus beta mc square, and then psi, sometimes I write psi like this, so don't worry about this, that both are same. So if we will write it, okay, so taking the constant, these all are constant, so I will write it as minus iota h bar c, then this psi dagger, okay, alpha del, this nebula operator will act on this, okay, psi, okay, plus beta in this psi dagger, then beta mc square is a constant, so we can write also after that, so just write this, okay, and then in this mc square constant will be multiplied. So now we have written it like this. So let's call this as equation number 2, or better, is there any good way to write this? Okay. So beta you can also take in the left hand side, we will see it later. Okay, so let's write it like this. Then now we can take the Hermitian conjugate of this equation itself. Okay, the whole equation we can take the Hermitian conjugate. Okay, so if you take the Hermitian conjugate of this whole equation, write all the terms with their conjugate and replace iota by minus iota. So in the left hand side, taking, let me write this, taking the Hermitian conjugate of equation, this is the equation 1. So if you take the Hermitian conjugate of the equation number 1, so one thing you have to keep in mind that when you take the conjugate of a product like AB conjugate, then you write it as B conjugate, not conjugate, dagger. Okay, so B dagger, then A dagger. Okay, like this is also for the inverse. AB inverse of a matrix is given as B inverse A inverse. So similar fashion you write the Hermitian conjugate of a product. So whatever is there in the left, we have to take the conjugate. So replace iota. Everything in the left will be conjugated. Like iota will be replaced with minus iota, then h bar, del over del t, then psi dagger. Okay, then this will be equal to the conjugate of this. Okay, so let's first write in the multiplied form, then we will take the conjugate. Minus iota h bar c, okay, alpha into del operator acting on psi, okay, plus beta m c square psi, okay, and then the conjugate of the right hand term. Okay, so this will give you the conjugate of this term, but minus iota will give iota h bar c. These are the constants, but alpha, del and this psi, the conjugate of this, plus this beta m c square psi and the conjugate of this. Okay, so this we will write as I h bar c, and this is basically the operator, so conjugate will basically replace the whole thing. Okay, take this as one entity. Okay, so we will write it as del psi dagger, okay, multiplied by alpha, not this. Okay, so let me, so it will be alpha dagger. Okay, so alpha will go in the right hand side. Okay, plus in the similar way we can write this as, but mc square is, these are all real, so we will call it as mc square, then psi dagger and beta dagger. Okay, so we have written like this. So now you know that we have to multiply it by its conjugate, not by psi, not its conjugate. So we will multiply both hand sides by psi. Okay, so it will be minus iota h bar del over del t psi dagger psi equals iota h bar c del psi dagger, okay, into alpha dagger, then psi, plus mc square psi dagger beta dagger, then psi. Okay, so you know that we have already proved that the alpha dagger is alpha and beta dagger is beta. So now it's time to utilize those results. Okay, so we can write it as, or we can call it equation number 3 first. Okay, and what we are going to do is we will be subtracting equation 3 from equation number 2. Okay, and let's say what we get. So from equation number 2 we have this term in the left hand side. Okay, so this is I h bar, okay, psi dagger, then del psi over del t, and then this term will be subtracted. So negative of negative will give you a positive I h bar del psi dagger over del t multiplied by psi. Okay, so this actually this should be written as separately as this. Okay, so this is the left hand side, and in the right hand side you can check that what is in the right hand side. These two terms, psi dagger beta psi, okay, this term, these two, and mc square, this will subtract, so this will actually cancel out when you subtract, so no need to write. Only we have to worry about this term. So let's write first this minus iota h bar c, minus iota h bar c, okay, psi alpha del psi. Okay, we have written the first term from equation number 2. Now we will subtract this term from third. So this is minus iota h bar c del psi dagger alpha dagger psi. Okay, so if you closely see these two terms, we can take out I h bar, okay, and then this is psi dagger del psi over del t plus del psi dagger over del t. It's look like the derivative of a product. Okay, so better we can write in the next step as I h bar del over del t of the psi dagger psi. Okay, and in the right hand side what we have minus iota h bar c. Clearly this we can take out as common. Okay, so this is psi alpha del psi plus del psi dagger alpha dagger, but now we can write alpha dagger as alpha. Okay, so better let's replace it now. Okay, so replacing alpha dagger by alpha, we now have what we have is psi. We have psi left. Okay, so now let's see what simplification we have done already. So if you closely see this, you will find that this can be written as minus iota h bar c, and the gradient of this term psi alpha, I think there was side dagger, and we have not written it. This the first was with a dagger. Okay, so this is having a dagger. This must have a dagger. Okay, so psi dagger psi. Okay, you can check this by taking it as the first term and taking this as the second term. So when you differentiate it, the first term, the derivative, you can differentiate like this. Let me do this for you. Okay, so when you differentiate, you will put it as the first term. The side dagger, take the derivative of this, so you can write it as del of psi dagger, then write it as alpha psi, then the first the derivative of this term. Okay, so psi dagger and del of alpha psi. So let's see, is it matching with it? So now this term matches with this. Okay, is it matching or not? So because alpha is a constant, okay, so we can take it to the left hand side and we can write it as psi dagger, okay, alpha del psi. Okay, although it is a matrix, but it's a constant, all the terms are constant, so we can take it to the left hand side. So this term matches with this, and let's see, is it matching? So this term is also matching, so that's why we have written like this. Okay, so so now we can cancel out this IH bar both hand side, and we can write it as like del over del t, okay, of psi dagger psi is given as minus c, because h bar is already cancelled, del of psi dagger alpha psi. Okay, if I take it to the left hand side, so now we can write it as del over del t of psi dagger psi plus c, or write it like this, del of c psi dagger alpha psi equals 0. And if we try to match it with the equation of continuity, del over del t, del rho over del t plus del dot j equals 0. So it exactly matches with this equation, and we can say that this rho is nothing but this psi dagger psi, and this j is basically c psi dagger alpha psi. So now we have the density, this rho, okay, and this current j. Okay, it's like the flow of charge, flow of any quantity which is conserved. So this must be psi dagger psi, and this is the current j. So it look like the probability density is changing, but the total change is 0. Whatever is there is change in rho, and that change is equal to the flow. Okay, so that's why the sum is 0. So now one thing we can see, that if I write psi dagger, okay, what is psi? Psi r comma t is given as psi naught, okay, into e to the power I over h bar p dot r minus let me write clearly. Okay, P dot R minus ET. So if you take the conjugate, so psi dagger will be the conjugate of this. Okay, this will go in the left hand side. Okay, and whatever is written here will be in the left hand side. So we can write it as e to the power minus iota over h bar P dot R minus ET into psi naught dagger. Okay, and if I multiply psi dagger with psi, okay, so this will give these two terms. Okay, these will give you e to the power 0, and so this e to the power negative of the term. Okay, and psi naught multiplied by this psi naught into e to the power same terms. These two things will be other reciprocal of each other, so this will cancel out, and this will give you psi. No, we have missed one thing. This is a dagger. Okay, this psi naught dagger psi naught. So this is nothing but exponential terms cancel out, and we have psi naught dagger psi naught. Okay, so this is the density which is independent of the exponential term. This term is completely gone. Okay, and now we can find the j also. Okay, so j can be written as c, and we have alpha. Okay, so you can also write it in the same manner, c psi naught dagger alpha psi naught. Okay, in similar manner you can check that this dagger and the exponential terms will be cancelled, and we can write like this. Okay, so now you know that when we wrote the expression for energy E equal to C alpha P plus beta mc square. Okay, so if you closely see this, you will find that basically E energy is just a real number, and this alpha is basically a 4 by 4 matrix. Okay, so if it is being multiplied, P is the vector, okay, momentum vector. So if it is being multiplied with psi, so a 4 cross 4 matrix must be multiplied to a if it is multiplied to psi, then psi must be of this form. Okay, like there may be 4 terms. Okay, like you can call it A, B, C and D. Okay, so if this is psi, this is equivalent to, because 4 by 4 matrix must be multiplied with a 4 by 4 should be multiplied with a 4 by 1. Okay, so this should be the structure of the matrix of this psi. Okay, so wave function, it has 4 components. So psi dagger can be written as the conjugate of this, or okay, so we can write it as A conjugate, the complex conjugate of this, then B conjugate, C conjugate and D conjugate. This will be the psi dagger. And if you multiply with the both of them, we can find rho psi dagger psi, and that will be given by the multiplication of these two matrices, the row and the column matrix. multiplied by this A, B, C and D, and you know that this will give you A asterisk A plus B asterisk B plus C asterisk C and plus D asterisk D. And you know that when a complex number is multiplied with its conjugate, the A is a complex number multiplied with its conjugate, this will give you a real number. So obviously this sum will definitely be a positive definite, and this solves the problem which we encountered in the case of the Klein-Gordon equation, when the row was not positive definite. Row could be less positive or negative, but in the case how Dirac wrote the energy expression, relativistic energy expression, in the manner C alpha p plus beta mc square, so that expression gives you rho, the probability density here, as a positive definite value. So this basically it overcomes the difficulty encountered in the Klein-Gordon equation, and Dirac equation has become a physically acceptable relativistic wave equation. So this way Dirac was able to solve the problem of having a positive definite probability density for a relativistic case or relativistic particle. Okay, so we will go further into this by we will see about how the Hamiltonian commutes with the orbital angular momentum or not, because we will see that it will not commute with the Hamiltonian, and this will give you this gives an intrinsic quantity called a spin to the to this relativistic particle. Okay, so from the Dirac equation it spontaneously gives you a quantity called spin, which is required for every relativistic particle, for this relativistic particle to have, and this we will see in our next lecture. Thank you.